Okay, so welcome back to the series of lectures on molecular spectroscopy for the Department of Chemistry, University of Lagos. In this video, we will be looking at Raman spectroscopy, the basic introduction to Raman spectroscopy. So, Raman spectroscopy, that's a technique, it's a spectroscopic technique. Remember, spectroscopy, we study matter, the various energy levels present in matter using electromagnetic radiation. So Raman spectroscopy is named after an Indian physicist. So it's the technique that is usually used to determine vibrational modes of molecules, although you can also detect some other rotational and low frequency or low energy modes that are present in the molecule, but in chemistry it's majorly used for vibrational modes. It's based on what we call the Raman effect or the Raman scattering. And the Raman scattering, that is inelastic scattering of photons by matter. So, meaning that there's an exchange of energy. So what is the inelastic scattering? Scattering in itself is a redirection of light by matter. So this is light over one frequency, monochromatic light. It encounters an object and it's scattered. So you see the different colors. Some are scattered that were the same color, so same frequency of the incoming light, and some are scattered at different colors. So when it's of the same frequency, when the light scattered is at the same frequency, then we say it's elastic scattering. This hardly gives any information about the molecule. However, the scattered light, like the red, blue, and yellow, can be over different wavelengths or frequency. That's compared when you compare that to the incoming light, and then you call that inelastic scattering. So Raman scattering or Raman effect is an inelastic scattering of photons or of light by matter. So after light interacts with it, and then it scatters. After light interacts with the molecule, and then the molecule scatters the light. Because of the different energy levels of the molecule, the inelastic scattered light is studied in the technique called Raman spectroscopy. The basic theory behind spectroscopy is that electromagnetic radiation that oscillates at a particular frequency V has, like we said before, electric component and magnetic components. And the electric component is given by this amplitude multiplied by sine 2 pi frequency t. The molecule also has electron cloud. Electrons are negatively charged. This electron cloud can be distorted and by electric field, and since the electromagnetic radiation has some electric components, it can also distort it. When the electric field distorts the molecule, it induces a dipole other than the permanent dipole or absence of it that may be in a molecule. So whether a molecule has a permanent dipole or not, the electric field upon its interaction with the electron cloud can induce a dipole. So for example, if you look at this charged particle, in the presence of the electric field, there's a redistribution of how the positive charge is being felt. So the induced dipole is given by P equals alpha E, and our E is given by that equation, where alpha is called the polarizability of a molecule. The polarizability is the ease of distortion of electron clouds surrounding a molecule. It's different for different molecules, and it increases with science. For the helium atom is 0.2, and for the acetylene it's 4.5, as a matter of fact, alkanes have high polarizability. So it's given by, so the molecule itself, whenever it's vibrating or rotating, the frequency of the polarizability can be given by alpha being equal to alpha naught, where alpha naught is the average or equilibrium polarizability, plus beta sine 2 pi v vibe. So the v vibe here is the vibrational frequency, is the frequency at which the molecule, let's consider the vibrational mode now, is vibrating. If it's a rotation, then it's the frequency at which it's rotating. And B is the rate of change of the oscillation with the particular molecular motion. Okay, so if we put this together, so we have our induced dipole, which is equal to alpha multiplied by E, given by alpha naught plus beta sine 2 pi v vibe t into E naught 2 pi v t. So this is the frequency of the incoming electromagnetic field or laser light. That's the laser light is the one often used for Raman spectroscopy. So if we put this together, so we have alpha naught multiplied by the electric field, so this is here, and then this other, the second part of, multiplied by the second part of that equation. So using trigonometric rule, which was supposed to come up somewhere here and it did not come up, using the trigonometric relationship, sine A sine B equals cos 2A minus cos A plus B minus cos A minus B. Okay, so we can expand this expression here, and expansion gives cos 2 pi v vibe minus vb minus cos 2 pi v plus v vibe t. So there are three components here. The first component E naught sine 2 pi v t. So this the particular frequency of this is the same as the incoming light, which is vt. So the light characterized by this expression is called elastic scattered light. It's at the same frequency as the incoming light. It's still scattered, can be in different direction, or it can be in the same direction, but it's scattered at the same frequency as the incoming light. And we see that it depends on the average polarizability than the electric field. It's called the Rayleigh scattering. So Rayleigh scattering is elastic scattering of light. Now let's look at this other section. So this is half b naught cos 2 pi v minus v pi, that's our focus, and the other part cos 2 pi into v plus v pi. So this includes, so you will see that the frequency has been shifted. So rather than just the frequency of the incoming light being scattered, we have frequency corresponding to v minus v pi, and another one corresponding to v plus v pi. Because they are different frequencies, we say that this is inelastic scattering. Inelastic scattering is called Raman scattering. Raman scattering. There are different types of inelastic scattering. Raman type scattering is a form of inelastic scattering. It depends on the amplitude of the incoming light and the rate at which the molecule is oscillating with its internal polarizability. This scattered light, we say, has shifted by v vibe, and this v vibe, I think in the next slide it will be clearer, corresponds to a vibrational mode in the molecule. So we're dealing with rotational, we'll continue to a rotational energy level more appropriately. So it corresponds to a vibrational energy level of the molecule. The component V plus V vibe is called a Stokes shift. That's because the frequency increases in energy. So a Stokes shift corresponds to an increase in energy. And this component V minus V vibe is called the anti-Stokes shift. It corresponds to a reduction in energy. So that's that. So a Raman spectrum now occurs. A Raman spectrum, so it's used to study all forms of molecular states. So a Raman spectrum arises when a photon is scattered from a molecule at a different frequency. So that's the basic Raman spectroscopy. So the scatter of a molecule at a different frequency. It can be scattered at a higher frequency. In such a situation, the molecule was in a lower energy state. The incident light shoots it to a virtual state, and the Raman scattered light that emitted is actually lower in energy than from here to the virtual state. That's because the molecule has absorbed some amount of energy. On the other hand, you can also have the lower energy shift, the molecule being already in an excited state and is forced to go down to the ground or to a lower vibrational state. So that's the anti-Stokes scattering. One major thing about a Raman spectrum, this is a sample of Raman spectrum. I think this is for carbon tetrachloride. So it often consists of the frequency of the scattered light, some frequencies to the right and some to the left. So the frequency of the scattered light, which is the frequency of the incoming light, sorry, not scattered light. Well, it's a frequency of the elastic scattered light. That will be the appropriate thing. So it's as the frequency corresponding to the laser wave number. It's called the Rayleigh scattering, as we said before. So it's at the same frequency as the incoming light. And then we have the Stokes shifted ones. That's to the higher energy, lower energy, because you have removed some part of the energy. And then you have the anti-Stokes. So it is noted that the Stokes Rayleigh is the most intense because most light are scattered at the same frequency. And the Stokes is more intense because molecules are coming from a ground state to a higher state than the anti-Stokes, which involves higher states back to the lower state. And because the lower state is usually more populated than the upper states. So what is measured in Raman frequency is the difference between the laser frequency and the observed frequency, the observed shift, which we call the Raman shift. So the Raman shift, so that's the difference between the excitation Weber laser line minus the observed frequency. Remember that the frequency part component is V minus V vape or V plus V vibe. It's usually reported in wave numbers delta V, which is equal to Vx minus V of that particular line, and which you can have as 1 over lambda x minus 1 over lambda I. This is the exciting wave numbers of laser line in wave numbers, and this is the exciting laser line in wavelength. So a quick example, the Raman line associated with the vibrational mode, which is both Raman and F, is found at this. When excited by a wavelength of 435, calculate the wavelength of the corresponding band. So the frequency of the exciting line, So we convert it to wave numbers. We're given in wavelength. And the wave number